do over here if I only have 6 bits, right? So we're going to have to put in some sign extension hardware here to facilitate this. So whenever we use an immediate number, and as I mentioned before, when we use constants generally in code, they're not usually very large. They're usually relatively small. So we don't have to encode a full 12-bit number in here. Now there's ways around this to kind of do this. And what's normally done in MIPS is you actually have 2 instructions that do this work to load in larger immediate values. But again, it's a rare thing. Again, we're using, when I talk about immediate numbers, it's like 0, 1, 2, 3, 4. Like they're usually small numbers. It's rare that they get very, very large. So that's a fair compromise. Okay. So as I said, there's a compromise that can be made for that limitation. So now our RAM address data path is now 12 bits because our registers are 12 bits. So our RAM will also be 4096 rows by 12 bits. Well, not by 16 bits like the ROM, but 12 bits in this case. Now, it should be noted that MIPS, when it started, was a 32-bit CPU. So with certain adjustments, we can make it all kind of work out that way. But you'll see here, this really doesn't change any of our hardware. Okay, so we're going to add in some new instructions as well. So a PDF has been posted there that with your student number, it has the opcode for your new instructions. So some of the new instructions we have are OR and AND. So those are R-type instructions. And we also have OR I and I. That's for OR immediate and immediate. And that's our new type, our new I-type instructions. Okay. Now, because we have to extend the data width of our immediate inputs, we kind of have to have some rules here on how we extend them. So the little figure here is kind of showing us what's happening. So before we would just take the immediate value and we would just stick it into the ALU, right, through a MUX. Now we're not going to do that because we have 2 options for extending this 6-bit value to get it to 12 bits. There's either a signed extension or an unsigned extension. So you use the extend block in Logisim, and when you set as signed and when you set as 0 to imply that the upper 12 bits will always be 0, and in this case, the upper 6 bits will always be 0, and in this case, the upper 6 bits will be a replication of the 6-bit going in from immediate. So this does a proper sign extension. So now we're going to have 2 outputs here that can go into the ALU, a signed extension and an unsigned extension. So your ALU is going to have an additional input. Okay, so the signed extended value will go to your add, sub, and borrow, whereas the unsigned one will go to your OR and your AND. All right, so again, just a small modification. All right, now, if you guys have any questions, just kind of throw them up there. So really, that's pretty much it. So yeah, inside your ALU, you're obviously going to have to add in the AND and OR gates in there. Again, you just use one set of gates and you just set it to 12 bits, and it does all the work for you. The ALU opcode, or ALU operation, I should say, is in the spreadsheet file that I've posted. So and the extra fields for the OR and the AND and the opcodes for the OR I and AND I are all there. All right. Now, as far as debugging and evaluation, oh, hold on. Is the due date supposed to be 2 days after assignment 6? Yes. Now, the reason I'm doing this is because I'm trying to kind of fit all these assignments into the limited time we have. And the problem we have here is that 2 of the labs that I still have to post, 10 and 11, have to be done in the last week of class. And therefore, they have to be done during the actual lab time. They can't be outside of that window. So if I kind of give you guys more time, not to say more time with this one, but if I try to keep it on this Monday schedule, there's not enough time to do everything. It's just one of those situations where, we're just lucky to have our labs on Mondays in the summer, where we have, at least 2 holidays, and in some years it's actually 3 holidays on those Mondays. So all those labs get postponed to the last couple days of the semester, and it really causes a lot of headache for that. Okay, but again, it doesn't really take that long to do. Okay, like these modifications are just sitting there changing these bit widths, and everyone kind of tells me the same thing, that it's, you know, historically they say it's not really a big deal. The biggest challenge is putting the code in. Now, I hope some of you, you know, maybe thought of you know, coming up with better ways to kind of implement the code. This is why we use assemblers and all these tools to do this for us. So if you consider using a spreadsheet or some other, you know, you could write your own program to do it, even better. You know, try to get into this idea of using computers for automation. These are wonderful tools. I use computers every day to make my life easier. And if you guys look at what you're sending me with these assignments, you know, there's 100 students each sending me multiple files, and you know, I couldn't do the evaluation of this stuff without computers. If I was doing this stuff manually, well, it just wouldn't be possible, right? Okay, all right. So as far as I'll show you the program, the testing code soon, but to kind of help us out here, this will be the last iteration, yes. To help us out here, we're just going to put just a basic counter in our design. It's not connected to anything, but it will have an output here, and the output will give us an idea of what cycle number we're on. So if there's a problem, at least we can kind of track it down. Okay, so we add in a counter, 12-bit trigger on the rising edge. We use a probe, so make sure this is a probe here, not an output pin. If you add output pins, then it's going to screw up your design when I try to evaluate it. Okay, and you can always change the radix of your probes. So I believe in this case I set it to hexadecimal rather than binary. If it's binary, you're going to have 12 ones and zeros. It's hard to read. The output pin order is the same as it was before. That doesn't really change. And again, don't forget the halt pin. Now, as far as the testing code, because we added, I tried to write a piece of code that's going to, you know, try to test everything, but you know, that's not always possible. But at least, you know, with the fewest amount of lines. So the testing code is essentially what it's going to do. It's the first part of the code. Each value of the RAM from addresses 32 to 36 in sequence are read and ORed by a single bit value, starting at bit position 0 and then rotating left until all the bits are on. So we're really kind of, you know, stressing this looping and you know, the modification of individual bits. And then the second part of the code, the same addresses are read and they're ANDed to remove a single bit each time. So it's setting a bit to 0. So again, starting at position 0 and then rotating left until all the bits are off. Okay, so the website does have a PDF showing you the expected values. So the cycle and values matches the simulation on the rising edge of the clock. So let me I'll just pull up that PDF just so you can see what I'm talking about here. Assignment 7. Okay, so for example, so on cycle 8, you'll see at memory address in the RAM 32, you're going to see this value here. Now, when I say 32 decimal or 20 hexadecimal. Okay, so you're going to start seeing these bits. So you can start seeing how, well, there's a 1 here, then another 1 appears here, and it kind of keeps filling up. So again, these are different addresses, right? So you'll see the other 32 here where we see this one here, and now there's a new one over here. And then the next 32, we're going to see a new one over here, right? So you can see the program runs for about just over basically 1,100 cycles. Now, you don't have to test all of these. You'll notice the pattern if everything is working, right? By the time you get halfway through the code, every value in RAM, there's not a lot of them, right? There's only, well, it appears 5, will have 1s in it. And then by the time it's done, those 5 that all had 1s in it will all have 0s in it. Okay, so if your code is working, or if your circuit is working and you encode this correctly, it should work just fine. I don't have a video of this playing because the preview window on the RAM is so small, it's kind of really jumping around. It's really kind of meaningless if you actually watch a video of it. Okay, but if you kind of, you know, run it for the first few times around and you see, okay, these bits are all being loaded in, or they appear to be loading in, then, you know, kind of fast forward to maybe this cycle here, check if these bits are right, and then fast forward to, you know, here and check if these are right. Okay. Because if something is wrong, given the number of cycles running and the fact that we're only changing one bit at a time, by the time you get to cycle number 528, if all 5 of these aren't ones, then something went wrong, essentially. Okay, I'll put that away. So as far as the actual ROM worksheet, I don't know why this got cut off, but sometimes it happens. Here it is. So you can see the code is longer. And because the CPU is, we've made it so these individual RD, RT, and RS are now 3 bits, you'll notice there's a thicker black line here going every 4 bits, right? So this is 16 bits here. The opcode is 4 bits, so I didn't break this up for you, but these are. So you can see how these 3-bit numbers kind of overlap on the 4-bit boundaries. So I kind of did that on purpose, so you can write in your binary numbers here and encode them in hexadecimal. Please be careful when you do this, because if you do put in the correct binary number but you encoded it improperly in hexadecimal, well, your program's not going to work correctly, right? So, and as always, I kind of put an example down here showing what you would get. So it might be, again, you can do this by hand, or you could try using, different tools. You can use spreadsheets to do this. There's a tool called des to hex, or I should say a function in Excel that does that. Right, you can kind of figure out what is all these particular values here. You can, multiply it by whatever power of 2 is necessary, and then, or all these values together, and then just kind of come up with the instruction number. It's actually pretty straightforward in doing that. That's how I did it. Or you could just write something in Python or whatever language you prefer. That kind of does it as well. But make sure it's correct. If it doesn't work, it's either the hardware or the software. But if you've done assignment 4 and that one works, and you scale it up correctly, then it will likely be a software problem. And if it's giving you an issue, again, just trace it one line at a time. Run the first instruction, check the value in the register, and say, did R1 go to 1? Okay, run the next one. Did R3 go to, well, 1? Then run the next one. Well, did R7 go to 48? Run the next one. Well, is R6 48 ORed with 5, for example? And if you see all these things are working, well, then find the instruction that doesn't work, and that's what the problem is. There's not really a better way to do that. I mean, you could write a more elaborate testing procedure, but then the code is going to be 3 or 4 times bigger. But it would tell you on, whatever line it would fail. So I've removed those sanity checks here in order to keep the code as small as possible. But it's really difficult to do something meaningful without a lot of code. It's really hard, right? Because CPUs can only do so much work per line of code. Alrighty, and I believe the last sheet, is just, there we go, is just an updated version that has the OR, the AND, and the OR and the AND as well. This will be the last time you do it. Yeah, I mean, you can obviously see why it's very tedious to be writing machine code by hand. This is why we like assemblers, because they do all that work for us. You're still writing machine code, but you're doing it in kind of like a humanistic way, right? So it's easier to write this that you see on these columns here than it is to like write this, well, just as binary bits, right? It's just our brains don't process this as easily as it would process this, which is totally understandable. But this is, what encoding stuff directly like this is what early programmers had to do. But when you only had a couple kilobytes of RAM, it wasn't so terrible. Right, so ALU out is the output of the ALU and not ALU 0. No, ALU 0 I don't really care about. We only process it when we're running branches, right? So in terms of the bits that you're coming out, I'll know if you process the branch correctly because I can see your current program counter or your program register. So the ALU 0 is really kind of meaningless. All right, so that's that. So this has all been posted. There we go. So if there's no other issues, I can move on to, I believe, chapter 6. All right, okay. All right, let's go to chapter 6 then. I'll close this. And as you can see, it's always on the wrong side. It's amazing. Technology. Okay, I'll put this over here, I guess. All right. So we're going to look more into how the HC11 works. And again, the HC11 is a purchasable device, and it's very common of what you would have seen at that time of microprocessor development. Even in fact, a lot of small processors, 8 bits, 16 bits, will still be CISC type devices. You can still find a lot of these derivatives, 6800, 6500, 80 or 8051. These are all, CPU numbers from different manufacturers that, they're still purchasable in some way. And some of these cores are still used in new items. For example, I think Cypress, they make a USB microcontroller where you can have it do, make it basically become any type of USB device, and its core is an 8051, which is an Intel-based microcontroller of the time. So it's still an active product, but they're using these older cores or CPU cores because they're very mature and there's a lot of tools for them. Okay. All right. So as I've said before, microcomputers and microcontrollers, they differ in many ways, but they all have one thing in common: the microprocessor. Its capabilities determine the capabilities of the microcomputer or microcontroller. So it provides timing control signals, fetches instructions, decodes data to transfers data to I/O devices, decodes instructions, performs arithmetic and logic operations, and responds to external I/O. So most of all the stuff that's happening in the microprocessor, we can't really see or have access to. Because it's just really a waste of space to bring out that information to the outside world. We only have a certain number of pins, and as I mentioned, the number of pins usually dictates the price of the product, right? So if it's a larger package, it's going to cost more money. More pins, it's going to cost more money, right? So we usually try to minimize that. The semiconductor wafer is usually, pretty small. I don't know if I do. Well, I can't get it now, but maybe the next day I'll show you. I have some. I don't know if you guys have ever seen the Arduino microcontrollers or boards there, but there's some where they have a DIP package. So you see this very large chip on there with like 14 or 16 pins, and they have some that are just like these little surface mount things that look like the size of, oh man, what could I even say it's the size of? It's like it's 5 millimeters by 5 millimeters. It's the same chip. It's just completely, in a different package, and it's, again, far less money for that version. But you can't sit there and connect to, the pins or probe the pins very easily, or change the chip if you like, right? It's just not possible. So we kind of give up this ability to access all that information because, well, the device should work. So the only way we can affect the device really is just through software only. So we can't, add, secondary inputs in that way or some other method. Okay, moving on. So here's our complete 68HC11. Let me move this over here now, I guess. Let's get a better view. So we can see all this kind of stuff that's going on now. If you guys have been working on the labs, you'll notice we have 2 accumulators, A and B, both 8 bits. We have index registers X and Y, so we can see those up here. We can see how they're kind of connected. Index registers X and Y are used to help us address memory with some type of variable offset. That's good for for loops and array references. We have a stack pointer as well. We need that to kind of keep track of what we're doing, where we've been. Any type of function call needs a stack to kind of do all that stuff. Our ALU is here. It has, we saw the data register before, we just kind of moved it over here because it's more centralized to the ALU. We'll also have a condition code register. This is various pieces of information from the ALU giving us some idea of what happened when we did our last, operation, so to speak. The timing control logic is all there. We kind of show the oscillator here, but that's just running the clock, basically running our system. And we can see the full set of input and output pins here on all the buses, right? So again, the timing control bus, that's basically just a hodgepodge of whatever's left outside of the address and data bus. So basically, our timing control logic basically tells all of these devices that you see here on these buses who's writing to the bus, who's reading from the bus, who's writing to the bus, who's reading from the bus, right? And where what you're reading is where it's going. So am I storing stuff to accumulator B, or am I storing stuff to accumulator A, right? So it's going to basically say all that. So and each one of these signals is determined by the microcode of each individual instruction. So each individual instruction, as we've seen, has a number of clock cycles that are required for it to fulfill its work. So this part of the circuit is actually probably the largest, although you wouldn't think it is by just looking at the block diagrams here. Okay. So all these little numbers here, in case you notice here, means it's 8 bits. This is 8 bits. The data bus is 8 bits. The address bus is 16 bits. So you'll see the individual registers up here are all broken up into high and low, right? So if we want to load any of these with a piece of information, it's going to take 2 cycles at least, because we have to put like the high version or the high byte first and then the low byte on another cycle. But then when they're together, they can actually just drive this bus all at once. Our data register is 8 bits, our condition code register is 8 bits. There's no surprise. You'll notice everything is a derivative of 8 or 16, right? Just makes the design easier. All right. So I guess in summary here, we have 5 16-bit registers connected to the internal data bus, our X, our Y, our stack pointer, our program counter, and our DAR. But again, they're shown as 2 8-bit registers each. We have 2 8-bit accumulators, accumulator A and accumulator B. And to kind of make the ability to do 16-bit arithmetic a little bit easier, and this is one of the changes they made later on, and that's why it's the 6811. So like, for example, the 6800 didn't have, I believe it didn't have an accumulator D, so this was something they added on later. Both of those can be referenced as the 16-bit accumulator D. It's not a separate register, it's just a way of looking at it together. So the system can say, okay, let's look at A and B as a 16-bit value. And as I mentioned, there's an 8-bit condition code register. We'll look at what's going on in there shortly. And all the expanded mode registers are shown as well. The expanded mode being the, I guess if you want to say, these latches over here, these buffers, and these signals as well. Now, if you just use the device in its internal mode, the built-in RAM would all be here, right? So you wouldn't really see these wires going in and out. And we could use these ports B and C as just static I/O. All right, so I have a couple clicker questions here to test your short-term memory. Let's see what happens, hopefully. Okay, I'm just kind of reviewing one of my emails here, and someone asked if they can get the marks for assignment 4 before assignment 7 is due. If your assignment 4 works, you should pretty much get full marks. The place you're going to lose marks is if something doesn't work. So please, if you submit it late, you'll definitely lose marks. If you don't zip the file, you'll lose marks. If you don't name it correctly, you'll lose marks. I mean, these are all preventable things. Yeah, apart from that, you know, usually what people lose marks on is that they know it doesn't work. They just submit it anyway. So it is what it is. So if you feel like, okay, if it doesn't work, but I'll submit it anyway, well, it might make sense to take a late on it and spend an extra day to get it working, because the late is only 10% per day. If it doesn't work, you will essentially get 0, depending on what's wrong with it. I try to go through it, find out what's wrong with it. I'll give you feedback, but I'll definitely give you that feedback before the due date for assignment 7. I believe the due date is, I don't know if anyone can check on that one, but I think it's July 16th or something like that. I can't really check right now. July 14th, yeah, that's what I thought it was, but I wasn't sure when the first day was. Okay, so it looks like 87 people is what we have here. So what is the size of the internal data bus? Well, the people who answered B is correct. The data bus is 8 bits. All right, let's move on. I'm not going to talk and explain more things because there are more questions and I don't want to give more things away. That usually happens. So another question here. This one should only take, well, it should take less than a minute, but I also want to stress with assignment 6 that I posted, do your work. You know, I don't care if you kind of work together to kind of come up with, you know, on labs and things like that, but please don't submit the same stuff. That's all I'm saying. All right, I have records of everything ever submitted to me since I've been running this course, which is well over 10 years. So every time you submit me a file, it goes through a rigorous comparative process with everything in the past. And you know, the computer basically tells me what are the most suspect things, and I kind of look at it manually and I can determine if someone got something from somewhere else. So if that's the case, you will be heavily or have many marks deducted. I'll just say that much. Okay, it seems we have 86 again here. There's 87. We'll move on here. So how many 16-bit registers are connected to the bus? If you guys remember, it is in fact 5. I don't know what else to say. Okay, so let's start looking at some of the specific stuff about the device. And again, this isn't just specific to the, you know, the HC11. You'll see this in other devices. Some information is given to us so we can figure out what's going on, or we can use these devices a little bit more more efficiently. So as I said, it's not necessary to understand the complete timing of the HC11 to program for it. We can obviously, you know, look at the book and see, okay, well, what's going on individually with these instructions, but and you know, from the perspective of understanding how the CPU works, that's good. But if you're just trying to get things working, well, we don't really need to know how, you know, what an LDAA does exactly. We just need to know that it's going to work, right? For example. So let's look at some of these control signals. So one of them, one of the very important ones, of course, is the reset signal. So during a power on reset, an external reset, these are 2 different events that can happen. The microprocessor is initialized and then copies the contents of these 2 locations in memory, FFFE, FFFF, into the program counter. So you can see over here, if this is what's in my, hopefully it's a ROM, right? Because the value stays. The FFFE goes into the most significant byte of the program counter, and the FFFF goes into the least significant byte, right? So this is where we get, okay, where do we start running our code from? So we have that ability with for this flexibility, because how much ROM am I going to have in my system? It all depends what your application is, right? So depending on this, let's say I have a 1 kilobyte ROM, then I might make this point to the beginning of that 1 kilobyte ROM. But what if I have a 0.5 kilobyte ROM? Then I might make it point there. So we always want the ROM at the highest point of memory, because that's where the most important piece of information is where do we go when the system resets. We certainly don't want that to be a RAM, because it could be anything. Now, another thing to note about when the system resets, and I'm pretty sure about this, is there's no guarantee on the values of the registers internally. So what is accumulator A going to be, or what is accumulator B going to be? They could be all something random. So you have to do something with those if you want to, use them. So assuming they're 0 is probably very bad to do. So you would formally set them to 0 and then use them, for example. Another nice feature this microcontroller has, and a lot of them do, is something called this is what Motorola called it, computer operating properly reset, or a COP, or a clock monitor. It's basically, there's actually 2 of them. There's a clock monitor as well, but it's there's these 2 vectors where the COP is basically a timer that counts down, and if you don't formally reset this counter through a special way of doing it, you can't. It's not just you just write one piece of information to one place in memory. There's a way to do it that if you don't reset this timer, when it hits 0, it will automatically reset the system. And what this is there for is to prevent the system from kind of, what happens if it goes out of control? What if there's a programming error and it starts running rogue code? And what's going to make it go back to normal, right? So if we don't reset this timer, the system will automatically reset. Now, the reason it has a particular way of resetting the timer is because, like I said, what if you just have to write to one register to reset this timer, one place in memory? Well, what if when the program goes out of control, it kind of does that anyway, and it does it frequently? Then this isn't very useful, right? So there's a particular process to follow, right? So I've seen a number of devices over my time where, normally you see a device and, it has like a light that tells you it's on. But does that mean it's working, right? So I've seen other devices where they have a light telling you that there's a power on, and then there's a flashing light. And if the light is flashing, it means it's working, because the software is actually flashing the light. If the software isn't working correctly, it would never get to the code that flashes the light, and you wouldn't see the light flashing, and that would be some indication to you that something is wrong with it. So just by looking at the device, wherever it is, and you say, well, why isn't the light flashing? Then you know something's wrong. Okay, so it's kind of like, that type of thing. Now it also has a clock monitor, which is an interesting thing. So if the clock is running irregularly or something like that, that can also run some type of piece of code to do something about it. What the end result is, it all depends on the application. So there's a number of features here which can help to stabilize your system. I've used all these features in my past experience. Again, these devices could be used in all different places where the environments can be poor. Maybe the power is poor. You might get a dip in power, and that could cause a problem. You guys may have heard of brownouts before. Blackouts are pretty good things because power is removed completely, and then power comes back and everything is fine. A brownout is actually really bad because power could be removed just enough to cause the system to be unstable but still function. So brownouts are a particular issue. Has anyone here had to reboot their internet router from time to time for no apparent reason other than those things just weren't working, so I just rebooted my internet router? And you had to reboot it you couldn't just hit a reboot button, you had to unplug it and plug it back in. So I'm seeing a couple people say yes, because those little power adapters you put in the wall, if there's a dip in power, maybe all of a sudden your device isn't getting 5 volts, it's getting 4.5 volts, and that 4.5 volts just happens to not switch a bit somewhere, and all of a sudden your system is somewhat tainted. And that's the worst kind of problem, because it's still working and you think it's working, right? So yeah, brownouts are kind of the worst things. Blackouts are good because there's no power. It's been gone for a while. Any charge in the capacitors is gone, right? So when it powers back up, it's all good. No brownouts. Those are concerning. So it's good now. They have power supervisory circuits that will detect that. You have to buy them, of course, if you're building a system where it will detect brownouts and formally issue a reset if it does detect it, or wait till the brownout passes. But these are certainly things that you have to be aware of. There's an interesting story about the Raspberry Pi 2. I remember reading about. So they had a power management circuit there, and when the Raspberry Pi 2 came out, people were like, "Oh, let's put this on a blog somewhere on a web page." And what someone figured out was every time they took a photograph of the board, the system would reboot. Any thoughts on that? How could that happen? Well, it's definitely bad, but why would that happen? You just took a photograph. How could it know there's a photograph? So what was happening? I'll give you a little bit more of the background. Well, there was a flash. So the flash looks like just light, but there's different wavelengths of light. So these particular flashes were emitting a radiation where the power reset circuit was not properly protected by this radiation. So the Raspberry Pi people are, they're always trying to find, well, what's the cheapest components we can put together to do this? And they got a really cheap power management circuit that was not tolerant to that radiation. So something so simple as that, right? So now if you put the device in a properly insulated box or something, that wouldn't be an issue. But as I said, different types of energy can cause weird things, right? So we have to be aware of that. So they weren't. Well, we'll say that. Okay. Other things. Some of these control lines. Well, we've seen some of these before. The address strobe. That's asserted when the low order address is present on the data bus, so we know what to pull off of port B. The E-clock, that's provided to us. It's telling us the operating frequency of the microcontroller, and we know that it's 1/4 the frequency of the XTALs or the provided crystal. So if you use an 8 megahertz crystal, you're going to get a 2 megahertz E-clock. The read and write, that tells us the mode for the external memory that's going on. LIR, this is a really useful line. This is basically telling us when the microcontroller is reading an instruction or if it's reading data, right? So it's like asserted low when it's an instruction, because normally when it's always grabbing information from memory, you just don't know what it's grabbing. So this kind of gives us a little insight there, and why this is useful is because we can actually build a debug circuit with this. So you can have it so when it loads an instruction, it kind of could assert an interrupt, and then you can use that interrupt to kind of cause a debugger to happen under certain conditions, right? You can kind of enable it or disable it. So it's kind of a neat way to create a hardware debugger. Now, as far as what are interrupts, I did talk about these before. There's two of them. There's an IRQ line, stands for interrupt request. That's a typical term you will see. It's asserted low by external devices to get the microprocessor's attention, right? So it's basically just some way to say, hey, something's happened, go find out what it is. So when this happens, the program or the CPU saves the current program counter and all the registers onto the stack, and then it jumps to a location provided by, well, these memory addresses here, and then that location is where you put in a piece of code for it to investigate what happened. And then there's a formal way to return from an interrupt where it restores the state of the CPU, and it just kind of keeps running things as it did before. So the best analogy I can use for an interrupt is you answering a phone call. So let's say you're expecting a call. Do you sit there every second picking up the phone and saying hello, expecting to hear someone? That's not, a very efficient use of your time, right? That's what we would call polling. You're constantly polling your phone, and I'm talking about a landline here. Just makes a little bit more sense. Where you just kind of you're always checking to see if something is there, and it's kind of a waste of time. Whereas it would make more sense to have, I don't know, your phone ring to get your attention if you're doing something else. So let's say you're, writing something, the phone rings, you pick it up, you talk to the person. you finish your discussion, you hang up the phone, and you go back to what you were doing. That's exactly what an interrupt is, right? It's some way of getting our attention. We investigate what happens, and we fulfill that, and we go back to whatever we were doing before. And the thing that we were doing before is kind of, it doesn't know that an interrupt happened, right? Why would it? It's just not important. But what's important to know is that whatever we're doing there shouldn't be timing sensitive, because if it is, we may not want an interrupt to happen. Okay, so let's say you're playing a video game and someone calls you on the phone. You would probably certainly press the pause button, right? But what if you didn't press the pause button and you're talking to the person on the phone, ignoring the video game? You're probably going to lose, or something's going to happen, right? So with interrupts, we do have the option to disable them. So we can actually tell the CPU that if an interrupt comes in, don't process it until I say you can, because I'm doing something really important right now. Okay, so this is a very useful thing. Okay, and we're going to use these quite a bit in our programming of this device. Now, there's another type of interrupt called an XIRQ. And this is traditionally, you'd hear it called an NMI interrupt, or non-maskable interrupt. And it's very similar to an IRQ, except it cannot be disabled. Okay, so now the term non-maskable was changed to XIRQ for a particular reason. And the basic reason was, and this was just a rare event that could happen. What if your non-maskable interrupt was asserted while the device was starting up? So you go to run your reset code, but you can't because the non-maskable interrupt has been asserted. So you can't even run your first line of code on your CPU. So it goes and says, okay, let's go run this code for your non-maskable interrupt. So it wants to save the program counter on the stack and all these things. The problem is you haven't had a chance to initialize your stack pointer. So that's kind of a bad thing. Where is it going to save all these PC, or the program counter value, and all your register information? It's got nowhere to store it. So it's basically an extremely bad time for this to happen. So a lot of older devices are actually susceptible to this problem. So Motorola fixed this by saying, okay, the XIRQ is essentially, it can't be disabled, but it can only be disabled in the first little bit of when your system starts up. So you have to initialize the system and then it's active. Okay, so they had to kind of change the term so people were aware of that. But this is certainly something that can go wrong. You have to watch out for these corner cases where weird things can happen. Okay, so once this is functioning, you cannot avoid this type of interrupt. But it's for something that's extremely important, right? We used to have, this is when computers were definitely more reliable, I suppose. I used to have workstations that would they would have the power supply was designed so that if you cut the power, there was at least 5 seconds of power where the system would know you cut the power, and it would kind of like flush out all the information of the hard disks and then turn off. So it had enough time to kind of save that information. And now modern day hard disks actually do have this. So if you actually pull the plug on a modern day hard disk, it's got enough power stored on there where it can kind of flush out its cache and make sure everything is good before it stops working, right, until there's no power. Because if you stopped a hard disk in the middle of a write to a sector, that sector is going to be bad. Like something's going to be wrong with it. Like the sectors have to be written completely, just like flash memory would. If you don't write it completely, there's some, the process has been interrupted, it's not completed, and some of the bits won't match up. There's like, CRC bits and all these types of things that make sure your data is correct. If that stuff isn't written correctly, then the sector is considered bad. And we certainly don't want that. Has anyone had a bad sector on a hard disk in a while? Believe me, that happened a lot of times many years ago, many years ago, but now things have gotten much better. Okay. All right, so we know that our microprocessor is always transferring information from one register to another. It's doing all of its work. The number of registers, or sorry, the number and types of registers impact the programming required for a given application. So you've seen with the HC11, we have a limited number, and this is typical of CISC processors. So that number is variable, but it's pretty much, the same in terms of, the way things work, how we use these registers to do these things, right? So registers are used to store data, addresses, instruction codes, other information about the current microprocessor state. So some are used as counters to keep track of the number of times a series of instructions was performed. So accumulator A and B aren't really designed to be counters. They're designed to be used for adding stuff, whereas index register X and Y are really designed to be counters and offsets to memory references. Okay, so let's look at some of these registers. I'll just kind of go through it a little bit more specifically, well, I guess for these ones. The program counter, that's always contains the memory address of the next instruction the microprocessor is to fetch from. So it's not accessible externally, but many instructions cause the program counter to change sequentially, and some can change it completely, right? Branches and jumps. We don't need to read what the program counter is because we know where it is. We put the program in memory, right? So it's kind of not necessarily useful to do that. The DAR, the data address register. On some systems, they often call it the memory address register or address latching register. Sadly, there's no consistency with this terminology. It is what it is. And it's used to hold the address of the data that the microprocessor is reading or writing to. So whenever we go out and grab something from memory, that's going to hold that information, right? That's like the final result of whatever that memory reference is. Okay, and I showed an example of that, I think, a couple chapters ago. The accumulator, that takes part in most operations. In many operations, the accumulator is the source and destination. As I mentioned, we have two 8-bit accumulators, accumulator A and B, and accumulator D is referenced as the concatenation of accumulator A and B. Okay, so if I were to change accumulator D, then I likely changed accumulator A and B, but if I change accumulator A, then I changed accumulator D, or if I changed accumulator B, I changed accumulator D. They're not two different things, they're the same things, we just refer to it differently. All right, so accumulator A would be the high byte of accumulator D, and accumulator B would be the low byte of accumulator D. So why is this useful? Because we actually have instructions, for example, where I can add accumulator D to index register X because it's 16 bits as well, right? But I don't have an option to add accumulator A or B to index register X because, well, one is 8 bits and the other is 16 bits. That's not really allowed. All right. So D is useful for some things. It just makes some programming a little bit easier, a little bit quicker. Yeah, so the problem with ACC is that some people will confuse it as just being accumulator, right? I mean, these are the things that our brains might do. Right, it's like calling something, why don't we call things 1 and L? Because people confuse ones and L's. They confuse zeros and O's, those types of things. So we try to avoid that confusion. Our brains are good when we're fixing things like words, but when it's very, technical information, it can cause problems. Okay, now in general, other CPUs, like our RISC processors, they have general purpose CPUs or general purpose registers. So the HC11 has no specific general purpose registers. But if it did, or we could use them we could use the other registers as well for just, temporary storage, those types of things. So with RISC processors, all registers are created equal. So register 1, register 2, register 3, and so on. They're basically all the same. There's nothing special between them, and that's one of the advantages of RISC. But with CISC, because we're trying to make the program smaller, we would make opcodes that are particular to particular registers, right? So that's just the way it is. But you'll see in the book, for example, or the manual for the CPU, you'll see nomenclature like this. For example, load a general purpose register from memory. So M, this bracket means reference the value of M. so the address to get this information and put it into this register, for example, and this is store. You'll see the line is basically implying the movement of data. So at the for every instruction, it'll kind of show this type of thing graphically, essentially is what it's doing, to avoid the use of words, right? Not everyone who uses, these CPUs will, speaks English, for example, right? So just looking at this kind of stuff here, for example, this means increment GP by 1 and stored in, GP. Sometimes they have numbers here to specify the general purpose register, but this kind of says that same thing, right? So remember this funny thing when I was in a statistics class many years ago, and the prof made a joke. He was writing all this stuff on the board, and he says, "Oh, you think this is bad? You should see it in Chinese." And some people in the class went, "Oh, like, oh, that must be terrible." And it's like, and then he kind of looked at everyone and said, it's the same thing, right? Math is a language that's, doesn't depend on specifics of language, right? So that's why we like to see this kind of stuff, because it separates it all from that. Now in CISC processors, you'll often see increment and decrement because it's a very useful operation, and it's to some people it's Greek, I suppose, yes. We want to have these types of operations because they're very small in terms of code. So we'll often see those types of operations on the HC11. Whereas in RISC processors, there is no increment or decrement, because it doesn't make sense, because an add command would take up the same amount of space as an increment or decrement, right? So, okay, so we don't really see general purpose registers here, but they do exist in other systems. And that does make programming a CPU a little bit more challenging when it doesn't have them. Okay, so the HC11, as I mentioned before, has two index registers, both X and Y, and it didn't always, at least the 6800 didn't, it only had an X. So they added in the Y later, okay? But just to show you the difference here, so here's the opcodes for loading something from memory with the X. So this would say load accumulator A from index register X plus 4. So whatever that works out to, that's where I grab information from memory. Now this 4 here can only be an 8-bit value, and it's an unsigned value as well, so keep that in mind. Now if I want to use index register Y, well, if you look at the opcodes here, well, the last two are the same. So we have this special opcode, it's called a pre-byte, that whenever the HC11 sees it, it says, okay, I'm switching to a mode that whenever you reference X, it's now Y. And this is an easy fix for a problem that, well, when you run out of opcode space, how do you fix it? Well, we often put in these pre-bytes to fix that. So this is used quite often in CPU design because they need to add more stuff to it. So the problem is, however, if I want to use the Y register, and they added the Y register because people asked for an additional index register, but they didn't have room to add it, so this was the compromise. Put in a pre-byte so that anything that follows just this, for this instruction only, is referenced by the Y. So the obvious benefit is I have an extra index register. The problem is it takes an extra byte of code every time I use a Y register, and it takes an extra cycle to run this piece of code because I have to fetch the pre-byte, right? That's compromise. That's the way it is. Now, you may think this is unusual, but it's actually quite normal. So if you bear with me just for a second here, I will show you a great example of this, if I can find it. There it is. Okay, if I just pull this over here. Okay, so this is a real-world example of decoded. So here's the actual byte stream, and this is the actual decoded instruction. So you can see Intel stuff is pretty heavy in terms of what it does, and you can see how the instructions get pretty large here. So this is 32-bit code, and this is 64-bit code for the same program. I won't tell you what the program is, it doesn't really matter. But can anyone tell me where they see it? So this is referencing 64-bit stuff, but you can clearly see the opcode or the operands. There's not 64-bit pieces of information here. So what are they doing, right? Can you see can anyone tell me what the pre-byte might be for 64-bit operations? If you just kind of look closely. Now, they're not the same instructions entirely. That's not 89. Now, keep in mind that the 64-bit. So for them to make 64-bit, they didn't change the CPU. They just said, okay, let's just put in something that says, okay, this next instruction will be 64-bit. Yeah, it's 48. So wherever you see 48, so here's 89. It's a move instruction, right? Now we see 48 and 89. Well, this is move between registers. So this is move between registers as well, but it's also with some type of offset. Again, this is what CISC languages have. They have a lot of addressing modes where RISC doesn't. So we can see, oh, you put the 48 in front, now it's a 64-bit. You put the 48 in front, now it's 64 bits, right? So 8D is still load effective address, and we can see over here 8D is still load effective address, but because they put the 48, now it's a 64-bit operation. So what this allows the x86 CPU to do is mix 32-bit and 64-bit together. So for example, I still have push RBP over here is 55, and over here, now it's not called in 32-bit, it's called BP. So in 64-bit, they called so E is for extended, for meaning 32-bit, and the R is for like more than extended, meaning 64-bit. So it's just interpreted differently mnemonically, but you can see it's the same opcode, right? Weird. It's kind of a little weird, but it is what it is. So do 64-bit instructions end up running slower than 32-bit instructions? Well, there is some argument for that. Clearly, adding 32-bit numbers is faster than adding 64-bit numbers, correct? I think we can all agree to that. But what a 64-bit CPU can do is it can break up its ALU into kind of like two ALUs, and it can actually it can do two 32-bit operations at the same time as one 32-bit. So it's kind of hard to compare. It is difficult to compare. It all depends on application, really. Okay, but you can clearly see that the 48 being used quite a bit. So this is something that Intel does often, and a lot of CPU manufacturers do this when they have to add in more space. And when I show you the opcode map later on down the road, you'll see why they had to do this, because there's literally no room to add instructions, right? Okay. Just close this window over here. All right, so we have access to the Y, but it's going to make our code bigger. So we have access to 64-bit instructions, but it makes our code bigger. Do we care? Look how much memory you have on your computer now, right? Not so much of an issue. Okay, the condition code register. This has a number of bits. These 8 bits all mean something special. Some CPUs refer to it as a status register or a process status register, whatever you want to call it. So it consists of individual bits with different meanings assigned by the microprocessor. We sometimes call them flags, these individual ones. And these flags are examined during the program execution to determine the next sequence of events. Now, the ones that are important, the bottom 4, are related to the ALU, and the top 4 are related more to the system. Actually, well, this H is more to the ALU, but I'll show you what they do here. So the carry flag is basically the result of the carry from the most significant bit of an addition or a subtraction, or from a left or right shift. So if I add two 8-bit numbers, right, and there's a carry from adding those two 8-bit numbers, that's where it gets stored. Now, normally, if you add two 8-bit numbers, you're going to get a 9-bit result, but I don't have a 9-bit register, right? So what I do is I take the bottom 8 bits, I store that into whatever accumulator I'm told to store it into, and that 9th bit gets stored into the carry. So we can always find out, did this number get larger? Or that the carry flag is also the borrow flag when we do a subtraction. If we do left and right shifting and we shift a bit out, the bit we shift out becomes the carry, and the bit we shift in was the carry before we shifted it out. So that's also useful as well. So the carry does a lot of things here in CISC processors. It also allows us to kind of chain additions together. So I could really basically create any size addition I want. Even though I can add numbers in 8-bit instructions, I can chain those together and I could create a 64-bit adder, for example. It would just it just would require a lot of instructions to do it. Because I can take that carry and I can move it to another operation, and I can, kind of move it onward throughout the addition phase. If we're dealing with signed numbers, we have the overflow flag, and that tells us when we've added 2 numbers and it's gone beyond the representation allowable by our system, right? So overflow can happen if you add 2 positive numbers or add 2 negative numbers, right? So if I add the biggest negative number there is with the next biggest negative number there is, I certainly can't hold that in the space I have. So the overflow would go on. Now with each of these flags, they get set, but nothing really happens unless I say, okay, check the overflow or check the carry. So it's kind of up to me to decide to inspect them. So the ALU will update them, but it's up to me to inspect them. I can also formally set or clear them using these instructions here. So set the carry, clear the carry, or set the overflow, clear the overflow. Yeah. We also have the 0 flag, and this is set to 1 whenever any arithmetic or data transfer or manipulation result in a 0 result. Right. So if I compare 2 numbers, whenever we do a comparison, that's a subtraction. So we look at the result of the subtraction. If the numbers are the same, that will result in a 0 difference, and the 0 flag will be set, right? So we kind of use that for equality. So whenever we say BEQ or BNE, BEQ is measuring or it's checking the 0 flag. So if the 0 flag is true, then it means the result of the last comparison was equal. Whereas if the 0 flag is not true, a BNE would be used for that, right? If I want to check for that, or a branch if not equal. We also have the negative flag, and basically that's again when we're doing 2's complement work. It basically indicates the sign of any arithmetic, again, data transfer or manipulation. So n is basically the most significant bit of whatever number you're manipulating. So if you manipulated an 8-bit number, that would be bit 7 would be copied to n. But if you manipulate a 16-bit number with some 16-bit operation, bit 15 will be copied to n. So it's a quick way of us finding out if the number went negative or not. Again, that applies to 2's complement numbers. So really, overflow and negative really apply to 2's complement numbers, which is what we would use for our negative numbers. All right, what else is there? Okay. All right, so the other things in the condition code register, I'll just kind of skip to H for right now. H is what we call the half carry. And that's basically the carry that happened between bits 3 and 4 of an 8-bit operation. So half carry is only changed by addition instructions. And if we look at the data sheet of the CPU, we can look at every instruction. It'll tell us which ones change, which flags change. And this is used for correct for BCD addition. So if you remember years ago, I should say, but when you did DLD1, when we do BCD arithmetic, when a number is out of range, we basically add 6 to fix it, right? So we don't have to formally do that here. The HC11 can do that work for us, but it relies on the half carry. So that's that result. Apart from that, everything else is more system related. So I is for our interrupt mask. That tells the HC11 whether or not it responds to external interrupts or not. So if it's a 1, it means don't respond to external interrupts. And if it's a 0, it means it does respond to external interrupts. So we can set or clear that easily. So if I want to stop the system from responding to interrupts, I just do SEI in my code, and it won't respond to interrupts until I do a CLI. And then it will, whatever interrupt got queued up, it'll then run it. The X bit, this is for the X IRQ, and as I mentioned before, this is the only time we can disable the XARQ. Okay, even though you're not supposed to disable it, they only allow this within a certain amount of time, right? So it's initially set to 1, so that can that basically disables XARQs, but it can only be set to 0 once, right? So it's a bit that you can only set to 0. It's set to 1 on startup, but you can only set it to 0. So if you want to use the XARQ, you set up your stack pointer and then you set that bit to 0, and then that's it. It's on and it can't be turned off. And this one doesn't have an SEI or a CLI. You have to do a command, what's called tap, which transfers accumulator A to the CCR. It's just something you do so rarely, right? Why create an instruction for it? So this is an easy way to kind of do that. And the last one is the S bit, which is basically stop disable. It stops there's actually a command called stop from operating or occurring. And again, this can only be set by the tap. And it can only be set, I should note here, and I think in both of these cases, within the first 64 cycles of operation. Again, that's a security feature, right? You want it to happen when the system starts up. You don't want it to happen, accidentally by some rogue program that might have started running, or you accidentally started running data. That could happen. So this is, again, these are ways to secure our system. So again, this is a fully commercial device, so it's going to have these protection measures in them. I can say that earlier devices prior to the HC11 had a lot of issues with this kind of stuff. As I mentioned, the NMI thing is a problem that they had. So you could achieve CPU deadlock easily. It's very easy to do on earlier CPUs. They didn't have a method for determining undefined opcodes. They would just try to run them, and if it got to them, it would just crash the CPU, and that was it. It was done. You had to turn it off. So these ones they have far better mechanisms for this. Okay, we're coming up near the end of class here, so I think I have a couple clicker questions we can get through, and I got one more slide. Won't hurt to go through. Okay, so the condition code register, there's a lot of useful information in there. We're looking at that for our conditional branching, right? As I mentioned, just like the MIPS CPU or RISC CPU only could do one type of comparison, equal or not equal to. That was basically it. Whereas the HC11 has a whole variety of things. It has, for example, branch if carry is cleared. It checks to see if the carry bit is 0. Branch if carry is set. Is the carry bit 1? Branch if minus. Branch if plus. Branch always, for example, always branches. There's also branch never. Branch if greater than. Branch if lesser than. Branch if greater than equal to. Branch if less than equal to. It has those for both 2's complement and unsigned numbers. So it has a whole variety of these things, and they all check different types of these flags. It's sometimes a combination of them as well. Okay, so again, this is something that's often seen in CISC processors, a lot of different branching operations. Okay, again, you can look in the manual to see how many there are. There's quite a few of them. All right. Okay, so let's go through with these clicker questions, and then I will I'll end it for today. So let's see. The quicker you do them, the faster we leave. How about that? And just a reminder, masked is a term that implies can be disabled. Okay, are we almost done here? Just trying to respond to a message. Something going on. Okay, well, I'm going to stop it there. I think it was 87, but I'll stop it at 1.5 minutes. Okay, so which one of these can be disabled? And it should be the IRQ. All right. These other ones are just, you can't disable XIRQ all the time. You can only do it within those 64 cycles, and that's it. Reset, you can't clearly disable that. That's kind of implicit. So, all right, let's try the next question here. So when I say efficient, it would be in terms of well, it says it there in the question, space and speed efficient. And when I say large number of iterations, let's say at least 10,000. Okay, I'm only giving you 1.5 minutes. A lot of people aren't going to get it in. Oh, just got it. Okay, it looks like most people picked index register X, and that is actually the most efficient one because it takes fewer bytes than index register Y, or run faster than index register Y. Accumulator D is also 16-bit. We want something that's 16-bit, but accumulator D, I'll be kind and give that to people, but accumulator D doesn't have a quick way of incrementing or decrementing. We would actually have to formally add a 1 or subtract a 1 from it, whereas index register Y and X have an increment function. So just because that wasn't detailed, I'll give it to you for that. Okay, one more here. I think it's another one. Yeah, this is basically a true-false question. I don't think I got to give you 1.5 minutes for this one. How about 45 seconds? We're already over time a little bit here, so. All right. 55. Okay, well, 2 people didn't answer. All right, so. Well, when we add 128 and 129, I can tell you for sure we're over 255. So 255 is the limit for an 8-bit number, so we would definitely have a carry. So yes, it is a 1. Yes, so someone just asked if you can you can submit something on Blackboard as many times as you want. I only honor the last thing. So if you already submitted it, it's still before the deadline. Just feel free to submit it again. Okay, all right, so we're going to stop there. So yeah, work on your, please get assignment 4 in. I'm just going to wait a few days before I mark it, just because some people might submit it late, but I should have your results. I'd like to say by Monday, but it's a long weekend and I probably won't get too much work done, sadly, but hopefully soon enough. All right, so if you have any other questions, just send me an email or something. I'll be around today, especially if there's an issue with your CPU. All right. Other than that, have a good weekend, and I'll talk to you guys on Monday. Well, tomorrow's a holiday, and Friday the university is effectively closed, although you may have classes. So it is kind of a long weekend. I don't expect many people to be doing much on Friday. Well, again, the university offices are closed Friday, but the university is not. What can I tell you? I don't come up with the rules. It's just what it is when you have a holiday on a Thursday, or, well, I don't even know what it would be if it was a Wednesday or Tuesday, but whatever it is. Yeah, what can I say? You could have complained well early on, but again, some profs just don't care or listen. Could be worse. It could be on Friday or sorry, Saturday night. That's happened before. Anyway, all right. So I'll see you guys on Monday. Enjoy whatever time you have. Talk later. Oh, how the next few labs weighted? I have to see, because I was asked to throw in some other stuff in there, so I'm still working that out. For accreditation, we need some extra learning outcomes measured, so I have to kind of throw that in there as well. So things have to be rebalanced. But again, nothing over 20%. All righty. All right. Talk then.